Hello everyone. We are very much happy to give these webinars month on month, and I hope these webinars are helping you to understand more about our products. This time we are dealing with most of the recent T1E1 test platforms we have introduced. Today's webinar session will be presented by our CEO, Mr. Vijay Kulkarni, and Shashi Murthy from our US office. Around 30 years back, we started with the single PCI T1E1 cards, which had only one T1E1 port. Now, down the years, we have evolved to the most recent 16-port T-Scan 16 card. So today we'll be focusing on some of these T1E1 products, which we have released in the market recently, and we'll be providing you a brief insight into how these can be used in the real-world applications. I request Vijay to please take over from here.
Okay, thank you, Sanjeev. Welcome, everybody. We'll discuss our T1E1 test platforms today. And this, as Sanjeev indicated, this is how we got started. And the technology at the time, about 30 years ago, was primarily TDM, analog technology, and that's how we started out in the test platforms. We started off with applications or hardware platforms for a PC environment, and we've continued in that vein ever since, primarily because we recognized back then, I think we were a little prescient, that the PC technology, PC revolution, was going to be, increasing in power and performance and size and so on, and we wanted to take advantage of that, as well as take advantage of the screen capability, the visualization that the PC environment provided, so we've just basically kept with that idea that and adapted our platforms as the PC revolution has continued. Today we have a whole host of T1E1 test platforms, as well as platforms in the IP space, Ethernet IP space, as well as other wireless protocols and wireless infrastructure protocols. So we've expanded from just TDM to VoIP and IP and wireless. But today we'll focus on our TDM platforms, our T1E1, specifically our T1E1. We also make T3, 3, and Sonnet platforms for OC3 and so on. But we'll probably discuss that in later webinars. Okay, so here is a bird's eye view of our T1E1 hardware platforms. And you can see here that they come in various capacities. Some of these are, like for example here, this particular, so this is one of our legacy cards, but here our Express card with the dual interfaces, our Octal card with 8 ports. Each port is full duplex, so this provides for high capacity. This is one of our portable products that has a lot more than just TDM technology on it. This is our tProbe here. Here's another a very portable platform called our USB T1E1 Analyzer. And this one is our latest application or hardware-based platform, our T-Scan 16. It's a receive only, but it can handle up to 16 T1E1 ports. So these are our T1E1 applications. It's just a very short synopsis of our T1E1 applications. Actually, I was adding to this chart as much as I could before this presentation started. Now, you know that T1E1 applications are the foundation for most of the protocols that are out there in the telecom environment now. And it continues to be one of the basic foundations for transmission and switching and switching technologies. And I think all of you are familiar with T1 and E1. T1 is the American standard. That's 1.544 megabits per second. It's channelized, and it's also used in unchannelized applications. So we have channelized here and unchannelized T1E1 applications. E1 is the European version. That's 2.048 megabits per second, and they're mostly used all over the world, actually, standardized by the ITU. So
yeah, Vijay, we have not included DCME and ATM and a few other protocols.
right, yeah, probably. I mean, we probably
Yeah,
missed out on a lot of applications here under this slide, but surely.
Yeah, we can simulate and analyze voice, digits, tones, any
Right.
protocols, analog, digital, echo testing. That's another biggie. Okay.
Right. Yeah. And of course, I think one of the things that makes our T1E1 applications user-friendly and visual is that we have things like spectral analysis and oscilloscope displays that can actually take a look at the data in a variety of different ways that helps in diagnosis. But we also have, like Shashi said, ATM and PPP. PPP is used to transmit packet data over T1E1. MLPPP, which is used to take T1E1, multiple T1E1 pipes and use that for, again, packet environment. About 5 years ago, 10 years ago, we started, as the wireless revolution was taking place, that also started using T1E1 pipes as the foundation for transmission and switching. So a lot of the GSM, which is the 2G and the 2.5G technology, uses T1E1 transmission and switching for carrying the wireless protocols. I think you've heard of that as GSM-A, ABIS, GPRS, TRAU. Even some of the 3G protocols are using T1E1 transmission and switching technology. It includes UMTS and CDMA. Shashi, did you want to say anything more on this particular slide?
Yeah, all our T1E1 analyzers come with the record and playback data on the entire T1E1 or fractional T1E1, call recording and simulation. And you can simulate and analyze voice, digits, tones, protocol, echo, used for echo testing, and so on.
Okay.
Analog testing, yeah.
Okay, that was a good point, Shashi. So recording and playback. So one of the first things that we did with our hardware platforms is we made sure that we were the first in the industry to actually be able to record the T1E1 traffic. Whether it was one T1E1 pipe or multiple T1E1 pipes. So that was a very distinguishing factor at the very beginning, at the onset, when we started building our very original Super T1 cards, as they were called at that time. They were designed for, if you recall, the PC buses at that time, they were called ISA, ISA. And I think the PC platforms themselves were called x86 and 286 and 386. So we had built cards for all of those platforms. And believe it or not, we were able to record at those at the entire T1E1 rates on multiple pipes with those PC environments. Initially, they were DOS only, so our applications were purely DOS. But of course, we've graduated from that to all of the applications. That includes APIs for Linux platforms, as well as are very full-featured Windows platforms. Okay, so I thought we'll go through all of our platforms and try to tell you what the distinguishing feature of these platforms are. So our tProbe unit, this was something that we introduced, what, about 5, 6, 7 years ago. It's a very versatile unit. Okay, Shashi, did you want to go through these interfaces, all these features on this platform?
Sure. Yeah, this is our tProbe analyzers, and this one has the ability to add optional boards such as Datacom Analyzer and FXO FXS simulation. These FXO FXS are used by analog phone lines. This FXO port allows to simulate a two-wire FXO device such as a telephone or a fax machine. I mean, this is FXO port, yeah. This FXO port allows to simulate a two-wire FXO device such as a telephone or a fax machine. Using this FXO port, you can monitor analog data, a fax call, or a voice call on a two-wire line. And we also have this FXS port, which emulates network port, FXS service such as telephone wall jack, monitor aux, send ring signal, provide dial tone, all those things. Using MAPS application, we can simulate two-wire telephone port and telephone wall jack. Using FXO port, we can simulate phone, and FXS port, we can simulate wall jack. And we have VF interfaces here on these tProbe units, and these have variable impedances, and these can be connected to headset also. And various impedances are 135, 600, headphone.
And high impedance also?
A high impedance, yes.
Okay.
And then we have another good feature of this tProbe is cross-port through mode, which provides inline monitoring, which eliminates complex cabling. And if you set tProbe in the cross-port transmit mode, you can do drop and insert error. Again, this cross-port transmit and cross-port through mode, having these modes, this will eliminate complex cabling. I mean, you can add to it, Vijay.
Yeah, sure. We have a slide, follow-on slide that kind of explains that a little bit better. So we'll get to that.
Okay, another important applications are jitter measurement and analysis and pulse mask. This is how this tProbe unit differs from our old legacy USB analyzers. So as I said before, I mean, and this also comes with, we have optional boards. We have ability to add optional boards such as Datacom, FXS, and we can also change frequency offset plus or minus 615 Hertz. So we have the ability to change frequency.
Okay. Okay, so the other thing was, I think Shashi mentioned these Datacom interfaces, and we'll talk a little bit more about that later. All right, so we had mentioned cross-port through and cross-port through and cross-port transmit. This is the cross-port transmit mode. I think Shashi mentioned that in the cross-port through and cross-port transmit modes, what happens is whatever is connected to one of the ports goes directly through the relays to the B port. And in addition, you can actually monitor the receive side signal. Whatever comes in on A goes directly to B, and whatever comes in on B goes directly to A. So all you have to do is...
this is good for inline monitoring.
Right. It's very useful for inline monitoring. It reduces cabling. So if you wanted to connect our tProbe analyzer between two devices, A and B, you have to momentarily disconnect A and B and connect them to these to our dual ports, and then place the ports on through mode and A and B are instantly talking to each other as before, and you can be monitoring the traffic. And so we're talking about these two ports right here, the T1, E1 ports. Okay. Cross-port transmit allows the same thing. This is a little bit of a busy diagram, but it'll give you the concept that A can be talking to B, but you could also insert errors, for example, or drop and insert VF, or in either direction. So, for example, from the A to B direction, you could route the A signal through in this direction and back out to B. And if you wanted, you could insert errors, insert a VF signal, drop and insert data without disturbing the other time slots. So as you know, T1 and E1 are multiplex signals. There's 30 channels in E1 and 24 channels in T1. So you could be you could be A could be talking to B across all of those channels except for one, and you could be possibly intruding on just one of those channels. Maybe it's a test channel, for example. So that would be the way that this cross-port transmit would be used. Okay. So this is our VF option on the tProbe. And Shashi, do you want to talk about this briefly?
Yes, in the VF options, we can insert VF data and also drop, and here are the different VF interfaces that you can set to, VF impedances you can set to. We have not shown everything, but you can set to high impedance and also headset and the 600 normal standard and 135 ohms and 150 ohms, all different impedances, different resistors values.
What we just talked about earlier about drop and insert time slots, this is this feature is also available on this VF dialog bar. So it's always in any of the channelized applications for T1, E1, sometimes you'd like to listen to the audio signal, and of course this allows you to actually listen to the audio signal. There's a built-in onboard speaker or that VF jack, which can be fed to a outboard speaker, and you can actually listen to the audio and verify that that there's, if you're doing testing, you can verify that there's actual speech. If there's a fax signal, you can listen to that, or a modem signal, and so on. So it comes in very handy. Okay, so this just shows you that the audio capability is available through this VF drop and insert, and it utilizes these mini headphone connectors.
3.5 mm.
Yeah, 3.5 mm, right. Okay. Okay, so one of the things that our platforms allow you to do is, as you know, the T1, E1 signals are high-speed signals, 1.5 megabits or 2 megabits, and each of those has transmits pulses in a unique format. In E1 it's called HDB3, and T1 it's called B8ZS. And these pulses are very narrow pulses, about 600 nanoseconds, something like that. And in a central office environment or at a customer environment, these pulses have to meet certain rise time and duration requirements, and our pulse mask display tells you what. So you can see here that the actual pulse falls within this mask. This happens to be an E1 signal, and we give you a graphical representation of the actual pulse as it is. We capture a pulse and we plot that pulse within this mask. The actual signals can also be varying very minutely in terms of duration and actual timing. So it might be 1.5 megabits, but it might be varying very slightly plus or minus, and it might be varying almost instantaneously. That's called jitter. It might, in terms of average clock, it might be okay, but it might be jittery clock. So this, our jitter measurement, allows you to make that jitter measurement, and there's also a jitter measurement mask.
Generation.
Right, for generation and for testing, you can actually measure whether that jitter that is received or complies with a certain mask. So we can actually generate jitter as well and see if the actual device under test can sustain a certain amount of jitter. So these are all device-dependent compliance type of measurements that allow you to test a particular device according to jitter and according to pulse mask. So the other thing that we can do is T1 and E1 signals vary in terms of frequency. 1.5 megabits is the nominal rate. 2 megabits is the nominal rate for E1. But equipment is designed to be able to withstand or tolerate a certain degree of offset from those nominal rates. And this allows you to actually test whether or not the device under test can tolerate those frequency offsets. Okay, so Shashi, this was you want to discuss the FXO port capability on the tProbe.
Yes, FXO port allows to, this is FXO port, and this allows to simulate a 2-wire FXO device, such as a telephone or a fax machine. So it connects through you can connect to a wall jack, which goes to the PPX, and
Okay,
goes to.
So here, here we have this FXO port here, which is an RJ11, and it's connected to the wall, which is a representation of an FXS port that's connected to a PBX, or it could be connected to the central office. And this FXS line will provide ringing and you know, all of those two-wire protocol. So a typical call here is shown that allows you to emulate. So the tProbe can emulate an actual phone, and this allows you to. And the phone can be any worldwide phone. So the actual it could be a European phone. We emulate all of these two-wire protocols. So we go off hook. We hear the dial tone, transmit the digits. The dial tone is interrupted because of the digits, and the far end is rung here, and we hear the ring back here, and so on. So this is the entire two-wire protocol. So of course, on 2 wires, this is at the subscriber end, of course, and this is still a dominant form of transmission, a dominant form of communication, landlines they call them. And even though wireless phones are taking over, I think landline phones are probably here to stay. Okay. So FXS is the counterpart, and this is, I won't go into the detail here, but this is the emulation of an FXS port. All right. So, you want to talk about all of the different protocols that our T1E1 platforms implement.
Yeah, these are the HTLC, MLPP. You can monitor HTLC, MLPPP, frame relay, ISDN, GSM, GR303, ATM, TRAU, PPP, CDMA, DCME. You can monitor between.
Okay, so Shashi is just going through a litany of all the protocols, but every protocol I think that's out there on that rides on T1E1 can be analyzed.
Simulated and analyzed. Yeah.
Right, simulated and analyzed. Our simulation platform is called MAPS, M-A-P-S, Message Automation Protocol Simulation, and that platform allows you to emulate HDLC, MLPPP, frame relay, ISDN, all of these protocols. Of course, GSM, TRAU, UMTS, these are wireless, GPRS, CDMA. TDM protocols.
Record anything that goes on this line.
Right. So we have our analyzers that analyze these protocols. They give you detailed protocol analysis, and we'll show you a screenshot of that later. And we can also emulate those same protocols using our MAPS platform, MAPS platform. So here's our typical protocol analyzer screen. This is for the MLPPP Analyzer. Okay, so MLPPP stands for Multi-Link Point-to-Point Protocol. And this is the method by which T1 lines, multiple T1 lines, or multiple E1 lines can carry packet traffic. Initially, when IP traffic was evolving, T1, E1 transmission lines were the dominant form of transmission. Ethernet was mostly restricted to the office environment. And the WAN environment used T1, E1 lines or T3 lines. So now T1 lines are only 1.5 megabits, or E1 lines are 2 megabits. And so they're not really that bandwidth, they're not large pipes. As you know, Ethernet packet traffic requires a lot larger bandwidths, 10 megabits, 100 megabits. So MLPPP is a way of concatenating multiple T1s and using those multiple T1 pipes to send packet traffic. And our tProbe or our Octal analyzers or our TScan 16, which is a 16-port analyzer, can look at an aggregate number of T1 or E1 pipes that are all being used for PPP, for packet transmission. And MLPPP is one of the standard methods of transmitting packet traffic over T1 E1 lines, multiple T1 E1 lines. ISDN Analyzer. Shashi, you want to talk about that?
Yeah, in the ISDN, you can monitor ISDN calls. Actually, under call detail records, if you bring up the call detail records, build call detail records, you can see calling number, call number. Sorry, we have not shown you here, but you can see all the details like how long the call lasted. And if you click on particular call, you'll see all the messages pertinent to that particular call, placing call, alerting, setup message, alerting, call proceeding. This looks like multiple calls, alerting call proceeding of one call, and so on. But you can see all the message types. If you click on a particular call that you are interested, you can see all the setup messages like setup message, alerting, call proceeding, and when it got connected, and all the details. And the second pane gives you the hex, all the lap delay details, all the protocol details. The third pane gives the hex dump of this particular message.
Okay, so the ISDN Analyzer, ISDN was the original, it says ISDN stands for Integrated Services Digital Network. So that was the first digital protocol that attempted to use T1, E1 lines for transmitting voice and data and video. And that was the first attempt prior to IP and ATM and all of those technologies. Initially, we had ISDN. And ISDN can also ride on multiple T1 lines. In that case, it's called NFAS, non-facility associated signaling. So we also analyze that. That's when multiple T1, E1 lines are used and only one signaling channel. ISDN carries signaling on one time slot, usually a 64 kilobit time slot that is on either time slot 23 for time slot 24 for T1 or time slot 16 for E1. And you can use one signaling channel and multiple T1, E1 lines, so we analyze that. TRAU, this is one of the wireless protocols that uses compressed codecs. They're called full rate, half rate, AMR, and so on. and it's a way of taking T1 E1 lines and using the entire bandwidth in sub-channel increments. In other words, instead of using an entire 8 bits of a time slot to transmit traffic, you can actually use 2 bits, which means that it's only using 16 kilobits per second, or 1 bit, which is 8 kilobits per second, or some variation of that. That way you can pack a lot of wireless traffic on one T1 line or E1 line, and allows you to also utilize these complex codecs and squeeze a lot of traffic out of the T1 E1 pipes. So we do that analysis as well. So this something like this would be very useful if you had a GSM network. You could use our TRAU Analyzer to listen to the hundreds of calls that are occurring on a T1 E1 pipe. Okay, so we talked earlier about the visualization and ability to show a lot of information on the PC screen, and this is one of the ways that we do that. This is byte values and binary byte values, and we can also show power and power here, frequency, DC offset. If you know what DC offset is, if you're sending voice, and voice signals are all AC signals, meaning they all have frequency components from 0 to about 4,000 hertz. If you're talking about mu law, A law. Now, one thing that you don't want is any sort of a DC offset in those signals, which could cause distortion, and this measures that, as well as signaling bits and power and frequency. And you can see the frequency in all of the time slots at once. Okay, so we have one of these Shashi, you want to go over this application, the call capture analysis application?
Yeah, I just wanted to show this using this call capture analysis application. ISDN calls or SS7 calls, they can be triggered, and we can capture them and do a full analysis using our VBA and CDR applications, which can go into an Excel file, and a lot of our customers are using this.
Okay, so this is a little bit of a busy diagram, but basically what we're trying to say here is on T1 E1 lines you have lots of traffic going on, like between a PBX and a central office, or between a PBX and a gateway. And there are always issues with calls. When you make a call, maybe the other party is not there, or
not answering.
Or not answering, or the call does not
here.
Right, or the call does not complete, or the digits are not transmitted, or once the call is completed, you can't transmit the in-band digits, or so many different intermittent problems are present in these hybrid networks these days when you have not just a TDM network, but a TDM IP or a wireless network in between. And so to diagnose these kinds of problems, this type of application is very useful because it can non-intrusively capture all the calls and all of the signaling associated with the call, and you can retrieve any one of those calls through a filtering process on the PC. And so you could be capturing thousands and thousands of calls over several days or weeks, and then analyze those intermittent calls. So that's what this application is for.
Analyze and listen to the voice.
So the protocol here could be ISDN or SS7, like Shashi said, or CAS. CAS stands for Channel Associated Signaling. That means that the signaling is transmitted using DTMF digits and signaling bits. So we support almost practically every CAS protocol, and ISDN variation and SS7 variation. So it's a very useful application. A lot of carriers like AT&T and Verizon and so many others utilize this application. Okay, so on the tProbe, one of the unique features of the tProbe, is a very busy diagram, but one of the unique features of the tProbe is the Datacom port. Now, prior to the IP world, data was transmitted using RS-232, 449, RS-485, X21, V35. These are all data interfaces. So prior to the IP revolution, these were the interfaces that were used by, for example, IBM. In their, if you guys are that old, SNA architecture, Systems Network Architecture, or DEC, which is using the DDCMP architecture. So all of these types of data protocols were used prior to the IP. They used these types of interfaces. And these interfaces are still very common, and especially they're common in the military environment and in the satellite environment, where where these things are still part either of the legacy architecture, or one of the advantages of a Datacom interface is you don't have to necessarily jump from 64 kilobits to 1.5 megabits to 45 megabits, which is T3. So the telecom rates are very discontinuous. So you jump from 64 kilobits to 1.5 megabits. Well, that's a big jump. And then you jump from 1.5 megabits to a T3, which is 45, or the E3, which is 34 megabits. Or the next jump up is even much higher. But in the satellite world and in the data communications world, you want finer gradations. So these data communication interfaces have their own clocks, and that clock can be anything in between 64 kilobits and a T1 rate or an E1 rate. So you could be sending at 512 kilobits or 128 kilobits. So these interfaces are very popular in frame relay, in the military environment where you want speeds in between, or in satellite communications where you can't just jump from 64 kilobits to 1.5 megabits or to a T3 rate. You want finer gradations.
Yeah, so you can go from 300 bits per second to all the way to 115.2 kbps or 16.3.84 megabits per second.
So asynchronous rates, I think you all know what asynchronous is. It's start and stop bits. So there's no clock associated with asynchronous. So we support, in asynchronous, we support
300 bits per second.
Yeah, from 300 to about, something like 115.
115.2.
Right. And in the synchronous rates, those are the rates that the legacy synchronous protocols we're using. There I think we go up all the way to 16 megabits per second for the Datacom interface. And many of the applications that we have for T1E1 are applicable to the Datacom interfaces. Now, one of the things that, if we go to our next slide here, okay, so this is just a depiction of what RS-232 or a Datacom interface looks like. It has a lot of these handshaking signals. So early on in the olden days of data communications, there was all of this handshaking that went on between a modem. A DCE is a modem. A DTE is a terminal. So our tProbe can act as a terminal, or it can act as a modem. And so if you want to debug a Datacom circuit, you want to be able to assume either end. And you also want to be able to analyze the handshaking signals that go on between a Datacom interface. So this shows you that we can emulate both sides. And you can also, just like we do in T1E1, you can actually analyze both directions.
Non-intrusively monitor both sync and async data.
Right, right. So here you can see that you can monitor the one direction and the opposite direction with these two interfaces. And this is male here, and this is female. and you can supply all the proper cables. Okay, so I wanted to mention very quickly, Datacom applications use different forms of line coding, and this is still in vogue in satellite communications and or in the military, where you don't want to necessarily transmit data and clock separately. You may want to transmit that embedded. In other words, just have one circuit, transmit data and receive data, and the clocking is embedded within that signal. So the transmitter in one signal adds clock and data and transmits that signal. That way you're saving on some wires. And the receive side extracts the clock and the data and separates them. So this is NRZ coding is one form of baseband coding. This is called baseband coding because it involves pulses and it's not modulated. So this is one. We also do Manchester. There's a whole variety of baseband coding schemes that are used to transmit over either a copper wire. Usually it's copper wire, but it can also be used on optical lines. But these are all called baseband transmission schemes. And you can see here that they embed both the bit and the clock. So here, this Manchester encoding has a transition when you're transmitting a 0, a negative going transition when you're transmitting a 0, positive going transmission when you're sending a 1. So in this manner, it's sending both data and the clock, and it's saving some circuits, some copper wire circuits. And believe it or not, this can be very powerful technique for saving wires in a transmission. So in the military environment, there's a variety of baseband codecs, and they're called Manchester, Differential Manchester, and they have a lot of names to them. Okay, so that's the end of our data communications. We're going to go to our next platform. And Shashi, you want to introduce this?
Yes, this is our PSCAN 16, which is used when there is a need for monitoring more number of ports. This is a high-density T1E1 board with 16 ports, 16 RJ45 interfaces. These are receive-only T1E1 interfaces, and we support both the Windows 7 and 8 systems. And these go into PCI expansion slots, and this is our record box with the RJ48 jacks, and record box and PCI board is connected through this MDR36 pin connector, 3M mini-D ribbon cable. That's what it's called. You don't have to worry about the cable, as GL provides card and record box. This is a card in the record box. So this PSCAN 16 is compatible with almost all the T1E1 receive applications that are available with our tProbe or other T1E1 boards. You can do channelized analysis such as ISDN, SS7, GSM, GPRS, UMTS, and spectrum, oscilloscope. You can also monitor alarms on the T1E1 lines. And you can analyze voice, data, fax, modem, echo. Also do VQT, voice quality testing. Unchannelized applications that can be monitored are ATM, PPP, MLPPP, frame relay, BERT, and so on.
Okay, so one of the things here that make this this card unique is we can squeeze 16 receive T1E1 ports into this small card, and the jacks, we separated the jacks onto this separate outboard box so that we can keep this this card, the form factor of this card, still small. And in order to do that, we had to go to this sort of miniaturization of the connector of the actual signals. So this provides you the standard RJ48 connectors. Each one of these supports two. So this is a special breakout box. Each one of these supports two receive ports. So unlike a normal RJ48, which would have both a transmit and a receive, this RJ48 has two receives, and two here and two here. So altogether we have 16 receive ports here that we are monitoring non-intrusively the line side or the equipment side of a particular high density T1E1 system. So if we go to the next slide, it's just another way of looking at it. And here is the advantage of doing using our T-Scan 16. You can be monitoring 16 T1s or 16 E1s, or the same thing as 8 T1s duplex. Each T1 has an east and a west direction. And in effect, by using our T-Scan 16, one of the cards here, one of these cards can be monitoring 384 channels if it was a channelized application. So that's a lot of time slots, and it's all done in a single PC. So a single PC, like an i5, i7, could be monitoring that many channels. And in E1, you're talking about 496 time slots in 16. But you could also put many of these T-Scan 16s in one PC. As you can see, it's a very small form factor, and it's using a lot of custom logic here. You can probably see this. These FPGAs here, and so you could easily put 4 or more of these T-Scan 16s in one PC. And since PCs are pretty powerful these days, one PC can be monitoring 1,536 time slots, or that many voice channels. And so where would you find an application for something like this? Well, you might be monitoring a network, a junction point, where you have a lot of traffic going from TDM to IP, for example, let's just say, and you want to monitor all the TDM traffic. You could use our T-Scan 16 to monitor all of these voice channels, or they could all have signaling on them, or like SS7, for example. And you could be analyzing all of the signaling on all of those time slots and feeding them to our centralized network management system, which could be analyzing all of this traffic. So this provides you a very dense application to non-intrusively monitor hundreds, if not thousands, of channels of signaling as well as voice traffic. So this is what it's capable of, and we have actually customers that are monitoring lots and lots of T1s and E1s using our T-Scan 16. So again, this is another our applications for the T-Scan 16. You could be monitoring a lot of protocols, both channelized as well as unchannelized applications using the T-Scan 16, and you could be covering a lot of traffic. And this is just a sample of the kind of traffic, both channelized as well as unchannelized, that you could be monitoring. So here's just another representation of the way you could be doing that with this breakout box that could be sitting on a rack in a central office or in a customer environment, and monitoring, recording. You could be recording traffic, you could be doing protocol analysis, you could be doing traffic analysis. So this kind of shows you how that we have actually two different ways of using this breakout box in between T1E1 interfaces. And one is this says this is the bridge mode, meaning that you could put this box in the middle between, for example, it could be a central office, channel banks, a PBX, a router, and perhaps some other entity on the other side. This could all be at one facility. Our breakout box basically allows you to send that signal through, send a particular T1 or E1 signal through, and we non-intrusively tap that signal with this breakout box and feed that through this dense connector to the PC. So this PC now is monitoring something on the order of 384 or whatever time slots or signaling channels, and this could be used for this breakout box can serve as in bridge mode. So in other words, it's non-intrusively monitoring this. Another way to use that in a customer environment, there may already be a DSX patch panel that is connecting the equipment to the line, and that DSX patch panel has been installed and available for use in monitoring. Well, in that case, you can connect our breakout box directly to the DSX patch panel via those monitor jacks that are there, and the breakout box goes into a monitor mode in that case. A monitor and bridge are very similar modes, but they're both non-intrusive, and they allow you to monitor the signals without disturbing the actual traffic. And it's a non-intrusive. And so in either of the bridge or monitor mode, you could be monitoring all of the channels that go on between the equipment and the line. And we're talking about that, up to 8 or 16 T1s or E1s. And this is then fed through this dense cabling to our TSCAN 16 board. Right, so there's a bridge mode and there's a monitor mode. Those are two ways to handle a customer environment, and our TSCAN 16 is compatible with both of those, and it's non-intrusive and allows one to easily use our TSCAN 16 in a existing environment and be able to monitor that many T1s and E1 lines. Okay, so this is the next platform. So this platform is for PC. Okay, so the PCs are now available in what's called the bus. Okay, so the PC bus has undergone a series of evolutions, right? So from early on, when you had the ISA bus and the PCI bus, and now the PCI Express bus, the USB bus, and the Ethernet. So all of these interfaces to a PC, we provide different platforms for interfacing across all of these types of buses. The prevalent bus in vogue today is the PCI Express bus. So you can get a rack PC with multiples of these PCI Express, and it's a very small connector that is capable of interfacing at gigabit rates to the internal PC architecture. And so this card is applicable for that.
Yeah, this is the PCI version of our tProbe, which goes into the PCI slots.
Right. And so another platform, Shashi, you want to talk about this?
Yeah, this is the high density card, high density with 4 ports or 8 ports. We can have a maximum of up to 64 ports.
So this differs from our TSCAN 16 in what way?
You can analyze and emulate. We can emulate also. We can emulate different protocols. We can record and playback or emulate and analyze different protocols.
Right. So this Octal board is both transmit and receive, just like our Express board or our tProbe or our USB analyzer. And it can do both transmit and receive.
These are high-density, high-speed cards, up to 64. Whenever there's a need for 64 ports in a single rack PC, and these can be used in the high-density PDM applications, ISDN and SS7, when you have to simulate hundreds or thousands of calls in single platform. Then you
Right.
can use
So we don't
these
actually have a
options.
picture. Okay, here it is. So here's the
Yes.
actual picture of a rack. If you can see this, right?
That's about 16 ports.
Right.
Yeah.
Here you can see what about two of
Two
these
Octal
Octal
cards.
cards here. So you could be emulating 16 T1s or E1s in one rack. You can actually be emulating a lot more. You could pack more of these cards into one rack PC and be able to do that. Okay. Comparison between all of the platforms, and so then you can probably look at all of this. It gives you a lot more detail as to how these different platforms are as similar as well as
USB
different.
and universal analyzers are our legacy products compared with the tProbe, T1E1 analyzers and express cards. And what it says is we have added cross-port through, cross-port transmit mode to make easy cabling with a drop insert and inline monitoring. I'm talking about this tProbe and dual T1E1 Express. And there's also VF interface with the microphone headset with different VF impedance. You can see all this comparison, and we have added optional boards such as FXO, FXS, and Datacom with the tProbe. That's the summary of all this comparison, but you can go into details if you're interested.
All right, thanks everybody. Appreciate it, and we'll probably meet you next week or next month on another webinar. Okay, thank you.